Good evening to all of you, and welcome to this problem solving session for the NPTEL course Foundation Engineering. So as you know that this course is basically instructed by Professor Kousik Deb from the Department of Civil Engineering, IIT Kharagpur, and myself, Shivshankar Nandi, one of the TAs for this particular course. And as per the information already conveyed to you, that I will be taking this session on each Sunday for this timing slot 5 p.m. to 6 p.m. 7 p.m. So the structure of this session would be as follows. So first we will be discussing about the concepts or the key points which we will be learning through the weekly lecture contents. Okay, so as you know that in each week we will be having 5 or something like that, 5 or 6 number of lectures. So first we'll go through that lectures, and at the end of this week, that is on Sunday, that is this during this time frame, we'll be discussing about the only the key points, or you can say we'll be summarize the concepts which we have learned or gained for this particular or through this particular week. Then we will be having some selective numerical problems, and these problems will help us in better comprehending the course. So in due course of time, while solving those problems, if you have any doubts or if you face any problems, you can stop me at any point of time and you can clear your confusion. Okay, and at the end of the session, we'll close this session by taking a few homework problems, and in the upcoming week, so I will basically I will be happy to know your status, whether you have you basically were able to solve the problem or not. Okay, so then we can successfully solve, or we can successfully start the next sessions with the homework problems as we didn't solve in the previous week. Okay, so this is the more or less structure of these sessions. So with this short introduction, we'll now begin our today's session. And as I said, that first we'll basically have a quick recap of the topics or the concepts which we have learned for this particular week, that is week 1. So I'll be very happy if anyone who is present here can tell something about the topics which I've learned so far. So can you please explain a little bit about today's topic? So without your active participation, it will be one way only. Okay, so it will be more straightforward for me, or more easy way to handle this kind of session if you actively participate with me.
No, so last week session I didn't attend, so I could not comment on this.
No, not the last week session. I'm not asking about the last week session. I'm only asking about the topics which we have learned from this week. So I hope that you all might have gone through the weekly lectures. So far I think 5 lectures are released on the NPTEL portal. So have you gone through that?
Sir, I am yet to gone through.
Okay.
Got registered.
Okay. That's yeah. Not a problem. Okay. Then I'll first briefly explaining the topics as per my understanding, which I have learned from this specific week. So first of all, we have brushed up the concepts or basic fundamentals of soil mechanics. So what are those? The grain size distribution, weight volume relationship, relative density, Atterberg limits, hydraulic conductivity of soil, effective stress, compaction, consolidation, and shear strength. So these are the some basics of soil mechanics. Okay, so without the concept of these topics, we cannot proceed further. So this is something an advanced level course, foundation engineering. So to solve the problems of the specific course, we need a very clear or in-depth understanding of these topics. Okay, so we'll discuss about more or we will discuss in details about these topics while solving a few problems during today's session. So next, coming to the topic of soil exploration, we have seen there are three methods by which we can conduct this program called soil exploration. Okay, before going to that, so can you please explain a little bit about what is called soil exploration or why it's needed in the context of geotechnical engineering?
To know the nature of soil underground,
Yeah,
so that we can design the foundation or any structure accordingly.
yeah, very good. So to design a safe structure, superstructure or foundation for a superstructure, we first need to know about the type of soil, what it is, this below the superstructure or below the foundation of the superstructure, and different engineering properties and so on, groundwater table, the location of groundwater table, etc. So the program or the investigations field as well as laboratory through which we can basically get or obtain this kind of information or data, those programs or investigations are collectively called as soil exploration. Now, how we can perform soil exploration? So for that, there are different methods which are listed in this slide. So the first one is direct methods. An example of that is test pits. The next one is semi-direct methods. An example of that is boring. And the third one is indirect methods like standard penetration test. Okay. So under the heading of indirect methods, we will learn about more methods apart from standard penetration. But as per the content of this week, we'll only discuss about the standard penetration test. Okay. So far, we have the knowledge only about the standard penetration test. So there are much more tests beyond the standard penetration under the heading of indirect methods that we'll learn in the successive or in the next few weeks. Now, this boring can also be classified under four groups. So the first one is auger boring, second one is wash boring, the third one is rotary drilling, and the fourth one is percussion drilling. So I will request all of you, so before attending this kind of session, please go through all the lectures which are released for this. Okay. So still I am assuming that you all have the idea. So what are the standard procedures to, yeah, I think someone raised a hand. Can you please ask what means what you were facing the problem? What exactly you are trying to ask? Someone has raised a hand. You can feel free to ask. Okay. So either you can use the chat box or you can unmute yourself and ask. Okay, sorry, I am not getting a response from your end. Okay, if it is fine from your end, okay, so then I can go further. Okay, so this boring can be classified into 4 groups, as I mentioned earlier: auger boring, wash boring, rotary drilling, and percussion drilling. And I assume that all of you know about the basic procedure by which this boring is to be done, and for a particular boring, it has some limitations. So it is not suitable for any kind of soil or for any kind of engineering application, specifically in the context of geotechnical engineering. Okay, that you should know very clearly. So for an example, I can take the reference of GATE 2003. Okay, so this data is basically taken from GATE 2000. So as you can see, there are 2 lists. The first one is list 1 and the second one is list 2. The list 1 dictates about the boring methods like auger boring, wash boring, percussion drilling, and rotary drilling. And list 2, this basically dictates about the field conditions. Now what we have to do? We have to basically match the entities of list 1 with the entities of list 2, so that this boring is basically suitable, means listed in list 1 is suitable for the field condition listed in list 2. So this question taken from GATE 2003. So this similar kind of question, for solving the similar kind of question, you should have the knowledge of this boring, the standard procedure, and its suitability for a particular type of soil or for a specific engineering application. So can you please answer to this question?
Auger boring is for shallow
Yeah.
foundation on highways.
Yeah, so is matching with 3 in list 2. Very good. So auger boring is basically suitable for exploration for shallow foundations and highways. So likewise, wash boring is suitable for what kind of condition? Field condition?
Below water table in all soil types.
Yeah, very good, very nice. So wash boring is basically particularly suitable for below water table in all soil types except hard soils and rocks. Then percussion drilling.
Boundary and gravel tree strata.
Very nice. So rotary drilling should match with option or list number 2, the entity number 2 in list 2. Okay, large diameter boreholes over 150 mm in size. So the final answer we can write in this fashion. So P is best fitted for entity 3 in list 2, Q 1, R 4, and so as you can understand, it's a very straightforward problem if you have the detailed knowledge of this kind of boring: auger boring, wash boring, rotary drilling, percussion drilling. Okay, it's basically an example which is taken from GATE 2003. And at the end of this week, we have started gaining knowledge about one of the indirect methods, which is nothing but the standard penetration test. And this is the IS standard. As per the standard, if you go through the standard, you will be getting the detailed procedure by which this penetration test should be performing. Along with that, you will be getting the idea of various kind of corrections which are needed to correct the field SPT value. Okay, so I will not spend much details about these procedures further. So those who have gone through the weekly lectures, very good, and those still pending for going through the lectures, so I will request all of you, please go through the lectures. Otherwise, this means the conducting this kind of problem solving session, the purpose of this problem solving session will be lost. Okay, so once you go through all the lectures and you have some basic ideas of these concepts, only then you can be better benefited by this session. Okay, so this is my sincere request to all of you, and I will expect your active participation throughout these sessions. Okay, till the end of this course. Okay, so now in this session we'll mostly solve a few numerical problems regarding the fundamentals of soil mechanics. Okay, so since we have learned a very little about the foundation engineering, except from this boring, means different methods for soil exploration, then boring and standard penetration test, so we'll confine ourselves in the specific week only to solve a few numerical problems from the fundamentals of soil mechanics. Okay, so still we'll at the end of the session we'll try to solve two problems concerning the standard penetration test. Okay, okay, so let's start this session. So the problem one, it's related to the weight volume relationship. So the problem one is basically defined as a sample of clay has the liquid limit and shrinkage limit of respectively 60% and 25%. If the sample has a volume of 10 ml at the liquid limit and a volume of 6.4 ml at the shrinkage limit, determine the specific gravity of the solids. So this is the problem given to us. Now we have to determine the specific gravity of the solids with the data given to us, like the volume of the soil sample corresponding to liquid limit and shrinkage limit respectively. And the liquid limit and shrinkage limit values are 60% and 25% for the given soil sample. So how can we solve this problem? Any idea? Okay, first let me know what is the definition of specific gravity of solids. So if we denote the specific gravity of solids as Gs, so what is the definition? What is the analytical expression for this Gs? It's nothing but the ratio of,
Weight by volume.
no, weight by volume, that is the definition for density only, no?
Specific weight of an specific weight of water.
So density of solids divided by density of water, or you can express in terms of unit weight also. So gamma is by gamma W. So this is the definition. So this is the, I am writing here the physical significance of this rotation. Rho s carries the meaning of density of solids, and rho W density of water, and this Gs is basically the specific gravity of the solids. Now please see carefully, very carefully, that this rho W we can take it as 1 gram per cc. Yes or no? We know, na?
Yes, sir.
So the density of water, we know that it's 1 gram per cc. So we can easily substitute this value in this analytical expression. However, we don't know about the density of solids. Now to determine the density of solids, we can again go through the very basic fundamentals. So it is the ratio of mass of solids divided by volume of solids. So therefore we need to know the mass of the solids, which is basically involved in this given soil sample and the corresponding volume of the solids. So if we know, then we can easily determine the specific gravity of the solids for this given soil sample. So for that, I am giving you some hint. So these are the three-phase diagram. These are the three-phase diagram. So the first diagram corresponds to the liquid limit, three-phase diagram at the liquid limit condition, and the next diagram corresponds to the three-phase relationship at the shrinkage limit condition. So as we know that this is the volume versus water content plot. Please correct me if I am wrong. Okay, so this is basically volume of the soil sample as whole. Okay, not limited to specific component of the soil like solids or water. So this is the total volume. And these boundaries are known as, this is liquid limit, this is plastic limit, and this is shrinkage limit. So if we reduce the water content, then the volume of the soil will be reducing, and after shrinkage limit there will be no such reduction. Volume will be constant. Do you agree with me for this kind of variation, volume of the soil versus water content? I think you should know about this kind of plot, no?
No, yes, sir.
So I have taken this plot from the very fundamentals of the soil mechanics. Okay. So now you know another very important point, that up to shrinkage limit the soil sample is fully saturated or what? It is partially saturated.
Partially. Fully saturated.
It's fully saturated. Na? Up to the shrinkage limit condition, the soil sample would be under full saturation, because all the pores which are inside the soil mass, that will be completely filled up by water, no air. Okay, so from the first diagram we can distinguish these two components. The first one is mass of solids and the second component is mass of water, and there is no mass of air. Okay, so total M is basically subdivided into MW1 and MS, or in the reverse way we can say MS and MW1 will constitute the total mass or overall mass of the sample. Now coming to scenario 2, so there is a reduction in the overall volume, as we can see from the problem statement. So initially the volume was 10 ml, now it's reduced to 6.4 ml. So for a transition from liquid limit to shrinkage limit, the volume of the sample is basically reduced from 10 ml to 6.4 ml. So obviously there was a reduction in which component? Solid or water? Which component? Since we have water. Since the solid component cannot change as long as the soil type is specific. It's not changing. We are basically dealing with the same soil. So there is no chance of reduction in the mass of the solid. Only the mass of water can change. And since we are talking about full saturation, so there is no chance of air also. Okay. So therefore, we can write in this way that the change in water, mass of water, this will be M W1 minus MW2, and this is nothing but M1 minus M2. Yes or no? This is MW, delta MW. This is delta MW. Delta MW denotes the reduction in the mass of water for transitioning from liquid limit to the shrinkage limit condition. So I am writing in this fashion. It's MW1 minus MW2. That means M1 minus M2. Yes or no?
Yes, sir. Yes, sir. Correct.
Yes, sir.
Now, please tell me, the sample has a volume of 10 ml at the liquid limit and a volume of 6.4 ml at the shrinkage limit. Now, how much reduction basically happens? 10 minus 6.4.
3.6 m.
So, and it should be multiplied by rho W. Then only we can get the mass. Okay, so this is volume. So volume multiplied by density, then only we can get the mass. So that means 3.6 into 1. That means 3.6. What? 3.6.
Gram.
Yes, 3.6 gram. So we know the reduction in the mass of the water. Now this is from the sample data which is given to us. So the volume of the sample is given at both the limits, liquid limit and the shrinkage limit. So from that, or employing or utilizing those conditions, we have calculated the reduction in the water component, mass of the water component. Now we can also determine this delta MW, but in a different way. How? We know that liquid limit is liquid limit. What is liquid limit? What is
Weight
liquid
of
limit?
water by weight of solids.
Yeah, so it's nothing but, I want to know that it's nothing but the water content of the soil sample itself. Na? So the definition of water content is basically MW1 divided by MS. Now what is MW1? What is MW1? MW1 we need to figure out from this equation, that is, it is nothing but MS multiplied by LL. Similarly, shrinkage limit, it would be MW2 divided by MS. So MW2, it would be MS multiplied by shrinkage limit. Okay, so please correct me if I am wrong. Now we'll substitute the values of LL and SL. So this is LL and this is SL. Okay, so liquid limit is 60%. So that means this is 0.6 times MS, and this would be 0.25 times MS. Then delta MW, it will be MW1 minus MW2. That means 0.6 minus 0.25 times MS. That means 0.35 delta. So we have determined this delta MW in two different ways. So first of all, we have determined it from the change in the total volume of the sample. So 10 minus 6.4 multiplied by the density of water. Okay. Yes or no?
Yes.
And so this will basically give you the volume of water, change in volume of water, then multiplied by the density, that will give you the mass. And secondly, we have determined it from the definition of the water content. Now these two should be equal. This delta MW of 3.6 gram and delta MW of 0.35 ms, this both should be equal. Okay, so this 0.35 ms should be equal to 3.65 gram. So from here we can easily determine the mass of solids as 3.6 divided by 0.35. So that means 10.29. So as you can see, we have already determined the mass of solids. So it's required for calculating the density of solids. Now the only component which we need to know, that is volume of solids. Now please tell me how we can determine the volume of solids as well. We have already determined the mass of solids. Now how we can determine the volume of solids? Any idea?
You can divide by density, sir.
We can divide the density.
Density, yes.
You were very correct, but still now we basically the objective of this problem is to determine the density only. So density is unknown, initially unknown. We are basically trying to determine the density only. So that's why we are determining mass and volume of the solids. So we cannot basically proceed in that way. So any other alternative idea? Listen, we know the total volume for both these conditions, liquid limit and shrinkage limit. Okay. Now, if we somehow try to figure out the volume of water, and if we deduct or subtract that volume from the overall volume, can we get the volume of solid?
Yes, sir.
Okay. So then we'll proceed in that way. And how we can determine the volume of water? Because we know the mass of water for both these conditions, liquid limit and shrinkage limit, from this expression 0.6 times ms and 0.25 times ms respectively. Now we'll consider any of these conditions. Okay, so we are considering the liquid limit condition. So MW1, this is 0.6 times ms, that means 0.6 multiplied by 10.29. So what would be the value? It would be 6.17 gram. Okay. Now, since we know the mass of water, we can determine the volume of water by dividing the density simply. 6.17 divided by 1, that means 6.17 milliliter. So therefore, the volume of solid would be simply V1 minus VW1. V1 is nothing but the total volume. So 10 minus 6.17. So therefore, it's 3.83 milliliter. So now it becomes very easy to calculate the density of solids, ms by vs only. So rho s, it's ms by vs. So ms we have got 10.29 and vs we have got 3.83. 10.29 divided by 3.83, so it would be
2.68.
2.68 or 2.69. Okay, so rounding up. Very good. So GS, then we can determine 2.69 divided by 1. So this would be the answer. Okay, so this is the way by which we can determine the specific gravity of the given soil sample for the prescribed condition. What are those prescribed conditions? The volume of the given soil sample concerning to water content, and which are nothing but liquid limit and shrinkage limit. Okay, so by employing the basic fundamentals or basic three-phase relationship, we can easily determine or we can easily address this kind of problem. So have you any problems so far? If not, then we can proceed further. Have you any problems?
No.
Okay, thank you. Okay, now we'll take our next problem. The relative compaction of a sand in the field is 90%. The maximum and minimum dry unit weights of the sand are 17 kilonewton per meter cube and 14.5 kilonewton per meter cube respectively. For the field condition, determine the dry unit weight of the sand and the relative density of compaction at the field. So, as we can see from the problem statement itself, two terminologies are utilized here. So, the first one is relative compaction and the second one is relative density of compaction or relative density. Now, can you please clarify me? Are these two terms are same? Means these two terms signify the same thing? Same physical entity? Same physical condition?
Yes, sir.
How? Explain a little bit. Please explain a little bit.
Sir, both tells about denseness of sand, soil.
Huh? You can go one by one. Okay. So first, define the term relative compaction. What is relative compaction? What is relative compaction? What is compaction?
Expels the air.
Yeah. So compaction is basically the process of densification of a soil through the expulsion of air. Okay, you are very correct. Now then, what is relative compaction? What is relative compaction? So it is nothing but the ratio of the dry unit weight achieved in the field divided by the maximum unit weight or density, whatever may be the case, obtained in the laboratory. So this is the ratio of field dry unit weight to the maximum dry unit weight. Is it correct? Is it correct?
Not get.
Not that. Then what is the definition?
Sir, not getting.
Okay. You are not getting. Okay. So this is basically, suppose when you will be constructing some highways, dam or earthen embankment. So before that, you need to compact the field. Yes or no? You need to compact, no?
Yes.
Yes.
So that compaction, for that compaction, you need to ensure or you need to achieve some prescribed condition. Suppose it's basically coming from the design that you need to compact the field with this unit weight at this moisture content. So if you can recall from the fundamentals of compaction, so then you will be visualizing that density versus water content graph. Yes or no? Can you please visualize? So this kind of plot, this is the density and this is the water content. So if you add water to the soil sample, so it will go on increasing, but after some time,
Optimum moisture content.
so this water content is called optimum moisture content. So after attaining the maximum dry density or dry unit weight at the optimum moisture content, if we add further water to the sample, then the density or unit weight, it will goes on or it will go on decreasing. Okay. So now from laboratory, you will be getting some maximum density for a moisture content, particular moisture content. Now, if you try to simulate the same condition in the field, will you be getting the same result? Whatever you are achieving in the laboratory, if you try to simulate the same condition in the field, so will you be expecting the same result or not?
No, sir.
So you will never get the same result. Okay. So you will be basically ending up with different unit weight or density at the field. So that means there will be a difference, and this ratio, whatever you are getting or achieving in the field compared to or with respect to what you have obtained or got from the laboratory investigation, that ratio will basically nothing but or will give you an idea of relative compaction. Now, more the relative compaction, more the magnitude or value of relative compaction, your quality control will indicate
Good.
positive, good, will indicate you are basically getting better result. So for this kind of application, basically there will be some prescriptions like that. You need to basically at least achieve this much relative compaction, something like 90% or 95%, or 100%. Achieving 100%, it's basically next to impossible. Now it's clear the definition of relative compaction: gamma d field divided by gamma d max. Now coming to the second terminology, that is relative density. Now what is the definition of relative density? If we denote the relative compaction by R and this relative density by dr. Now what is the definition of relative density? What is the definition of relative density? So it's nothing but
So it measures the degree of compaction.
It's measure the degree of denseness. It's measure
Compaction.
No, it's I don't know how you are basically utilizing the term compaction. So denseness you are basically getting from as a result of compaction only, but if you basically use this term in a very correct way, then it will be that it will indicate the degree of denseness, whether it's very poor or loosely packed, then medium, then dense, then very dense. So this kind of chart, I think
Okay.
you can get from the basic textbooks. Okay, so this is the denseness, degree of denseness. That is, it is basically less than 15%, then 15 to 35, then 35 to 65, then 65 to 85, and greater than 85, something like that. So very loose, medium, dense, and very dense. Okay. So in this way,
Yes.
depending upon the value of relative density, we can classify the granular or portionless soil into one of these categories. So it is E max minus E field divided by E max minus
Minus E minimum.
E minimum. Now you can easily understand from these two expressions that relative compaction and relative density are not same. These are two different entities. Now this relative compaction is related to directly given to us. This is 90%. And we need to calculate this relative density by utilizing this data 90% relative compaction along with the value of E max and E minimum. Sorry, E max and E minimum are not given. Instead of that, gamma D max of 17 kilonewton per meter cube and gamma D min of 14.5 kilonewton per meter cube are given. So we can calculate the values of E max and E min with the help of these two unit weights, maximum dry unit weight and the minimum dry unit weight. Okay, so we'll see how we can calculate this E max and E min by using these values. So first we'll address the first part of this problem, that is the dry unit weight of the sand. So the dry unit weight of the sand at the field we can get from the first expression. So relative compaction we know, gamma D max we know, so gamma D field we can easily determine. So it will be nothing but relative compaction multiplied by the maximum dry unit weight. Yes or no? We have to determine the dry unit weight of the sand at the field. So that means gamma D field
15.3.
and DR. Yeah. So 15.3, I think you have got the correct result. So this gamma D field, it would be R times gamma D. So that means 0.9 divided by 17, 15.3 kilonewton per meter cube. Okay, so first part we have already solved. Now coming to the next part, so we have to calculate the relative density. So the definition of relative density is E max minus E field or E natural divided by E max minus E. Now we don't know about the void ratios directly from the problem definition. Rather, we know the unit weights. Okay. Now, what is the relationship between void ratio and unit weights? Dry unit weights. So gamma D, we know that this is GS gamma W by 1 plus C. So therefore, we can get the void ratio as GS gamma W by gamma D minus. Do you agree with me? Do you agree with me?
Yes, sir.
Okay. So now we'll substitute this expression, the expression for void ratio, in this expression. So E max, so when we'll be getting the maximum void ratio for the maximum density or the minimum density? Now you have to be very careful when substituting this expression. The maximum void ratio, it will correspond to what condition? Loosest or densest?
Loser.
So that means the density will be minimum. So therefore, GS gamma W by gamma D minimum minus 1, and then again GS gamma W by gamma D field minus minus plus 1. So minus 1 and plus 1 will cancel out. So that's why I am not writing this one component here. So I am basically jumping one step, and then Vs gamma W by gamma D mean minus Gs gamma W by. Now we'll basically simplify this expression further. So if we simplify, then this would be gamma D field minus gamma D mean divided by gamma D max minus gamma D mean multiplied by gamma D max by gamma D. Please check very carefully the expression which I have got, is it correct or not? After simplifying this expression, are you getting the same expression for relative density?
Yes.
Okay. So now please see that all the terms are now known to us. So gamma D field already we have calculated as 15.3 kilonewton per meter cube. Gamma D mean and gamma D max are directly given to us as 14.5 and 17 kilonewton per meter cube respectively. So the job now to substitute the values in this expression only. dr, it would be gamma D field means 15.3, gamma D mean means 14.5 divided by gamma D max, that is 17, then gamma D mean, that means 14.5 multiplied by gamma D max, that is 17, and gamma D field means. So can you please tell me the end result?
Zero 0.355.
0.355. So that means 36%. So now what does it indicate? 36% relative density. So the soil belongs which kind of state? Very loose, loose, medium dense, dense, and very dense.
Medium.
Now if you know the range, that is, if I can recall exactly, so less than 15%, then 15 to 35, then 35 to 65, 65 to 85,
80.
and more than 80.
More than
Yeah.
80.
So this is for very loose, loose, medium dense, dense, and very dense. Okay, so you are correct. So though it is in the borderline, means 35, 15 to 35 and 35, so very close to borderline. Okay, so in this way you can understand the difference between these two terminologies, that is relative compaction and relative density. And it's very clear that both these terminologies are not same. These two do not indicate the same physical condition or physical entity. Is it okay?
Yes.
Okay. Now we'll take problem 3. So the problem 3 is about the calculation of effective stress. Okay, so first we'll read the problem statement. So the water table is at a depth of 5 meter in a silty soil mass of thickness 10 meter. Laboratory sieve analysis indicates an effective size of the soil mass as 0.015 millimeter. if the void ratio of the soil mass is 0.67 and the specific gravity of soil solids is 2.67, now if the silty soil mass as described above is underlain by a clay layer of thickness of 8 meter, what would be the effective stress at the middle of the clay layer? Assume the silty soil mass to be fully saturated in the capillary fringe zone and above this zone saturated to a degree of 66%. Properties of the clay layer are given as water content 25%, specific gravity of soil solids is 2.62, unit weight of water 10 kilonewton per meter cube. In addition to that, one constant is given as 45 mm square. So first I will try to visualize the problem, the stratified soil deposit, in situ soil deposit. So first of all, there is a silty soil mass of thickness 10 meter. Okay, so this is silty soil mass. Next, it's underlain by a clay of thickness, how much? 8 meter. Okay, and we have to calculate the effective stress at the middle of this clay layer, that is at a total depth of 10 plus 4, 14 meter from the ground surface. Now, what is the location of water table? What is the location of water table? It's
5 meter.
yeah. So someone raised a hand. So can you please ask your doubt?
No, sir. Instead of putting mic, I raise.
Okay. So this is the groundwater table. At a depth of 5 meter from the ground surface. So this is the ground surface. So this kind of stratified deposit we have. So first 10 meter silty soil mass. Inside this soil mass, we have encountered the groundwater table at a depth of 5 meter and the thickness of the silty soil mass is 10 meter. Then it's followed by or underlain by some clay of thickness 8 meter, and we have to calculate the effective stress at the middle of this clay layer, that is at a total depth of 14 meter from the ground surface. Now, what are the conditions given to this problem? So the conditions are like that. The properties of the silty soil mass. Okay, first we'll talk about the properties of the silty soil mass. So laboratory sieve analysis indicates an effective size of the soil mass. So what is the effective size? What do you mean by effective size? What is the effective size of a soil mass? It is nothing but the diameter corresponding to 10% percentage final, na? D10. So D10 is given as 0.015 millimeter. Then what is the void ratio of the soil mass? This is 0.67. And what is the specific gravity of soil solids? 2. Okay. Now coming to the clay, the properties given are water content 25% and the GS 2. Okay. And apart from the properties of silty soil mass and clay, additional data C 45 mm square and unit weight of water we can take it as 10 kg per meter cube. So we'll see why this information is given. It's the additional information, the constant value of 45 m². So can you please guess why this information is given to this problem, or what are the basic steps needed to calculate the effective stress at the mid depth of the clay layer?
Height and unit weight.
Height and unit weight. Okay, very good. So unit weight, it's not directly given to us, so we can get the unit weight by using the simple weight volume relationship. Yes or no?
Yes.
Okay. And then one statement is mentioned here that assume the silty soil mass to be fully saturated in the capillary fringe zone. Now what is capillary fringe zone? What is capillary fringe zone? Can you please recall the concepts of capillarity? Okay, so I am explaining a little bit. So the pores which are basically inside the solid particles, that pore can be visualized as a bundle of tubes of very small diameter. Therefore, though we are encountering the groundwater table at a depth of 5 meters from the ground surface, due to this tube, so it's basically based on the physics, okay, fundamental physics. So if you suppose this is some beaker and it's basically filled with some liquid, and if you insert a very small tube, then what will happen? Due to capillary action, this liquid will basically rise inside the tube, due to the surface tension. So the same phenomena basically will happen in this case also. So if the soil mass is very fine in nature, so above this water table there is a chance that this soil mass will be fully saturated, but up to a given height, and this height is called as the capillary height or height of capillary fringe zone, if we denote it as HC. And I hope all these things are known to you, okay? So it's nothing new to us. Okay, so this HC, up to this height, the soil mass will be completely saturated. Below the water table, there is no question, there is no doubt. So whether it is silty soil mass or clay, both the soils will be completely saturated. But above the groundwater table also, due to capillary fringe zone or capillary action, some of the silty soil mass portion will be completely saturated, and above that it will be saturated, partially saturated to a degree of 66%. So it's explicitly mentioned in the problem. So therefore, our first job would be to determine this height. By how much height this capillary action will be valid. Now, how we can determine this HC? So we can determine this HC by some empirical equation. Now, one of those empirical equations is given here, C by E dt. Okay, so that's why this value of this empirical constant is also given to this problem as 45 m². Okay, so please note that whenever we will be using empirical equations in any field of engineering or any other stream, we have to be very careful about the unit system. So what kind of unit system is involved in that empirical equation or deriving that empirical equation? And why that is very useful? Because if you substitute the values in a very incorrect manner, then you will be ending up with some erroneous result. So that's why this is very necessary to know about the unit system also. Now for this specific relationship HC, you will got this HC in millimeter when this D10 would be substituted, or D10 is in millimeter and C is in millimeter square. Only then you will get the HC value in millimeter. So therefore, we'll substitute this value 45 divided by E value is 0.67 and the D10 value is 0.065. Now, what would be the value for this HC then? What would be the value?
Four four seven 7.61.
447.61.
77.61.
Okay, very good. Millimeter.
Sir, it is 1033.29.
Okay,
Sir, you have written D10, here you have written 0.015, and in the
yes, tell me.
sir, you have put it wrong value, I guess.
Okay.
0.065
Ha,
you have
ha,
written here.
Thank you.
Yeah.
Thanks a lot for correcting me. So it would be 0.015. So 45 divided by 0.6.
Yes, sir, now it is correct.
4477.61 millimeter.
Yes.
So that means we can approximate this value as 4.5. Okay. So this height now equals to 4.5 meter. That means only this remaining 0.5 meter, because this is also 5 meter. So 5 plus 4.5, that means 9.5. So the remaining depth is 0.5, because the total thickness of the cell tissue almost is 10 meter. So out of 10, 9.5 meter is completely or fully saturated. So the partially saturated to a degree of 66% portion is only of thickness 0.5 meter. Okay, 0.5 meter. Now we'll go for calculating the unit weights. So first of all, for 0.5 meter, we need to calculate the bulk unit weight, since this portion is partially saturated. And for the remaining 9.5 meter, we will be calculating the saturated unit weight for cell tissue soil mass and place separately. Okay. So coming to calculation of unit weight. Calculation of unit weight. So first of all, we'll calculate gamma bulk. This is for cell tissue soil mass. Now how we can calculate the bulk unit weight? Sorry. The bulk unit weight we can calculate in this fashion, that GS plus AC divided by 1 plus C multiplied by gamma W. Now all these parameters are known to us because GS is 2.67, A's value is 66%, void ratio is 0.67. So now we'll substitute these values one by one. So 2.67 plus 0.66 multiplied by 0.67 divided by 1 plus 0.67, and gamma W is 10 kilo. So how much it is? How much value you are getting after calculation?
Sir, please show the previous slide.
Yes.
Sir, here you have written GS 2.62 and there you have written 2.67.
No. Please note very carefully that specific gravity of the silty soil mass is 2.67 and the specific
Okay.
gravity of clay is 2.62. Okay. Two different values are given to this problem. I hope it would be
18.63.
18.63 kilonewton. So similarly, you can calculate the gamma sat for silty. Okay. So let me calculate this part in the next slide. Gamma sat again for the silty soil mass. So here GS would be 2.67, saturated means 1, the E value is 0.67, 1 plus 0.67 into 10. So 20 kilometer per meter cube. And finally, gamma sat for clay 2.62 plus. Okay, so here the void ratio is not directly given to this problem, rather the water content and GS values are given, so we can easily calculate the values, the value for void ratio from this basic relationship, that is AC equals to WGS. So it would be 1 for full saturation, so that means 0.25 multiplied by 2.62, so that means 0.66. Please check. Have you got this void ratio for the clay?
Yes.
Okay. So now substitute. So 0.66, 0.66 multiplied by
19.75.
19.75. Very good. 19.76 after rounding. Okay. Now all the unit weights which are required to calculate the effective stress at the mid depth of the clay layer are with us. Now we have to be careful about the right substitution. Okay, so first we'll calculate the total stress suppose this is point A. So sigma A, it would be, so the multiplication of summation of multiplication of the unit weight and the respective height. Okay, so first we'll start from this partial saturation zone. So that means gamma bulk of the clay soil, so that is 18.63 multiplied by 0.5. Then the gamma saturated of clay mass, silty soil mass multiplied by 9.5. Then gamma sat of the clay multiplied by the respective height, that is. Okay, so this will give you the total stress at point A. If you calculate, then you will get this value as 278.36. Now, as you know, that effective stress is nothing but total stress minus the pore water pressure, okay, at the same point A. So sigma A we have got as 278.36. Now, what would be the pore water pressure at point A? What would be the pore water pressure? So I hope if you draw the pore water pressure distribution, then you will get something this kind of distribution. So it will start from 0 at the groundwater table, and it will follow a linear variation of gamma W multiplied by the depth. So where the depth is, so it is basically gamma W into H. So gamma W is your 10, and what is the depth from the groundwater table to the mid of the clay layer? It's 9 meter. That means, so
90.
90, yeah. So this is your 9 meter. So that means this would be 10 multiplied by 9. So we have to subtract 90 from
188.36.
so 188. So this would be the final answer. Okay. So in this way, we have determined the effective stress at the mid depth of the clay layer, and this concept is very much useful for the rest of this course. Okay. So whenever we need to calculate the this bearing capacity for a foundation, specific type of foundation, or the settlement analysis, we need to first calculate the effective stress. Okay. So if you don't have any problem, then we can basically take our next problem. But I will not, I think I will not be able to solve all the problems then, because already it's 6:23 p.m. Okay, and still 2 or 3 problems are pending for this session. So I will just briefly describe about this problem, and we'll go very quickly. Because
sir, one small doubt, kindly. Sir, this is how this is useful in field, sir. Just now you told me I could not get it. Kindly repeat it, sir. This whatever calculation we made. This is what is the stress at the underlying layer. So that is what now we have calculated. Okay, sir. In what way this is useful in field? Kindly explain this.
So basically, please see that this effective stress, whatever we have got at the mid depth of this clay layer. Now suppose you are constructing some foundation or footing over this ground surface, or at some depth below the ground surface. Now what will happen? So already there was some stress, in situ stress, and you are applying more stress through the construction of this foundation. And this foundation is basically taking the load or transferring the load of the superstructure to the inside soil mass, the below soil mass. So when you will design this footing, though this is not the part of this today's session, still I am basically explaining very brief about this. When you will be designing this foundation, means what would be its geometry, the length and breadth, width, or what would be the depth of foundation. So in that case, in a generalized scenario or in a broader perspective, you have to basically fulfill two aspects. The first aspect is that the foundation should not fail in shear. And what is the next? The next, that the settlement of the foundation should be under the permissible limit. So some permissible limits you will get from the Indian standards when you will follow that recommendations already prescribed or recommended in the Indian standards. So therefore, this foundation needs to satisfy these two conditions: shear failure criteria and the permissible limit criteria. Now, when you will be calculating this settlement, now settlement will be having different components: immediate settlement, consolidation settlement, secondary settlement, and so on. Now, for the calculation of immediate and consolidation settlement, or I think even, or I hope even in the case of secondary also, so you have to calculate the specifically for consolidation and immediate, you need to know the effective stress at the mid depth of that layer. Means the layers, and obviously this foundation will be having some influence zone. So it will not basically influence the entire thickness which is below the foundation. Suppose this is the foundation which I am talking about, and this is basically situated at a depth of dA from the ground surface. Now these are the stratified deposit. So this foundation will be having a particular influence zone, something like that. So the layers which we should consider for the calculation of bearing capacity and the settlement, not the entire layer. And why? That we'll know from the subsequent lectures. Okay. Now, as you know that for the calculation of consolidation settlement, suppose these two layers basically come into the picture for calculation of consolidation settlement. So this layer is basically sand and this layer is clay. So only this clay component or clay layer will basically constitute the consolidation settlement. Now, at the mid layer of this settlement, at the mid layer of the at the mid depth of this layer, you need to calculate the effective stress. So if you don't know how to calculate the effective stress, then how can you compute the settlement of this layer? So is it possible for you to calculate the settlement of this layer? Are you getting my point or not?
Yes, sir. Okay.
So that's in that way, the calculation of effective stress is very essential for designing a footing. Okay, so it will indirectly affect the design process, and
Okay.
it will be very clear from this immediate problem. Okay, so which we are going to solve,
Okay, sir.
at
Thank
least
you.
for the settlement calculation part, since we are not dealing with the design at this moment, since it's unfamiliar to us. Okay, so the soil profile at a site for a proposed office building as shown in figure 1 consists of a layer of fine sand 10.4 meter thick above a layer of soft normally consolidated clay 2 meter thick. So this is the stratified deposit talks about in this problem. So the first one is fine sand, then clay, and below the soft clay is a deposit of coarse sand. Okay, so 3 soil types are mentioned in this problem. The groundwater table was observed at 3 meters below the ground level. So this is the location of groundwater table from the ground surface. The void ratio of the sand is 0.66 and the water content of the clay is 34%. So these are the properties of the clay only. Okay, so please note. The building will impose a vertical stress increase of 160 kPa at the middle of the clay layer. So this is the additional stress increase which you are getting due to the construction of the proposed office building on this site. Suppose something here, the office building is basically construction of office building will take place, and this data is given to you that it will basically impose a vertical stress increase of 160 kPa. Estimate the primary consolidation settlement of the clay. Assume that the soil above the water table to be saturated. Liquid limit of the clay is 47%. GS is 2.67, and unit weight of water as usual 10 kg per meter cube. Now we need to calculate only the consolidation component only. Okay. Now how we can calculate this primary consolidation part? How we can calculate the consolidation settlement of this clay layer of thickness 2 meter? So for calculation of the consolidation settlement, we can take the help of this expression. Okay, so Cc by 1 plus E0 log of sigma 0 prime plus delta sigma divided by sigma 0 prime. So if you cannot recall this expression or the fundamentals of consolidation, then please go through the concepts once again. Okay, so it will be used again and again in the rest of this course. Okay, so this effective stress, consolidation, shear strength, these concepts are very much useful for comprehending this course. Okay, now what are the physical significance of these each entities? Cc, it's nothing but the
Compression index.
Yeah, very good. Compression index. E0, this is the initial
Void rate.
H, that is the thickness of the clay layer, and sigma 0 prime. Just now I was talking about this part. This is the initial effective overburden pressure. Okay, so before the construction or before the imposement of the vertical stress or before the application of the additional vertical stress, so this is the in situ effective overburden pressure, initial, and this delta sigma is nothing but the additional stress index. Now please note very carefully that this H, what is the value for this H from the given problem? What is the thickness of this clay layer? 2 meter, na?
Yes.
So this is 2 meter. And then this delta sigma, this is 160 kPa. And please keep in mind that this delta sigma is basically defined at the mid depth of the clay layer, as it is required to solve this problem. Then E0. Now what's about E0? The void ratio of the clay. Is it given to this problem? What's about the value for E0? Okay, so we can follow the same methodology as we followed in the case of problem 3. So we can calculate this E0 from this expression WGS. So W here is given as, what is the value for W? What is the water content of the clay? This is 34%, 0.34. And what is the value of specific gravity of the clay? So this is 2.67. That means the initial void ratio of the clay sample is 0.91. Okay. And what's about the compression index? The compression index, So for that, either we can determine this compression index from the slope of the pressure void ratio plot. So if you go through the constellation chapter, so you will be getting this kind of plot, E versus log of sigma prime. Okay, so this kind of plot you will be getting. So the slope of this plot will basically give you the compression index. Now this kind of data is not available with us, so we can determine the CC value from one of the empirical equations available in the literature, and I am writing one such empirical equation. So 0.009 multiplied by LL minus 10, and LL is nothing but the liquid limit of the plate, and it's mentioned as 47%. 47 minus 10. So what would be the value? Okay, so we know the CC, initial void ratio, thickness, and delta sigma. So the only component we have to figure out, so that is the initial effective overburden pressure at the mid depth of the clay layer. Now for that, we have to calculate the unit weights starting from the ground surface up to this part. Okay, as we have done in the previous problem. So now from onwards, this problem basically will be repetitive in nature. Okay, so I will basically quickly go through. I will not spend much time for this part now. Okay, so first we'll start with this sand. So for sand, we have to calculate two unit weights. So first, this for the first part means sand above the water table, we have to calculate the bulk unit weight. Okay, so is it basically mentioned somewhere that the above water table part we have to also consider saturated? Yeah, so this is mentioned here. Okay, so assume that the soil above the water table to be saturated. Okay, so that means we have to only calculate the saturated unit weight of the sand. Okay, not separately the saturated and the unsaturated part, since it's explicitly mentioned in this problem. So therefore, this gamma saturated for sand, again the similar expression, GS plus C divided by 1 plus C gamma W, because S is 1 here. Now what is the GS value? GS value, now we can take it as 2.67 for both the layers, because it's not separately mentioned for clay and sand. Okay, so GS will take 2.67 for both the layers, and the E value for sand will get from the statement. The void ratio of sand is 0.66. So 0.66 divided by 1 plus 0.66. Now similarly for clay, it would be 2.67 plus 0.91 divided by 1 plus 0.91. Please quickly calculate the values and let me know. So for sand, it would be 20.06 kilonewton per meter cube. And for clay, it would be 18.74 kilonewton per meter. So please correct me if I am wrong. So are you getting the same values?
Yes, sir, same.
Okay. So now we'll calculate the effective vertical stress at the mid of clay layer. Okay, that is, we can denote sigma 0 prime. Okay, we are directly determining this value, so it would be 3 plus 7.4, so 10.4 multiplied by what? The saturated unit weight of the sand, that is 20.06. So 20.06 multiplied by 10.4 plus 18.74, that is the saturated unit weight of the clay multiplied by 1, because we need to calculate the effective vertical stress up to this part. Okay, mid depth of the clay. So that means 3 plus 7.4 plus 1. Okay, then we have to deduct the pore water pressure. Similarly, the pore water pressure would be 7.4 plus 1, so 8.4. So gamma W into 8.4, 10 into. So please quickly calculate and let me know the value. I think it would be 143.36. Is it correct? This value 143.36.
Value correct, sir.
Okay. Okay, then now we can easily determine the consolidation supplement of the clay layer. So CC value is 0.33 by 1 plus E0. E0 is 0.91. Then H, the thickness of the clay layer, 2 log of sigma 0 prime. This is 143.36. Delta sigma is 160 divided by 140. Okay, so please calculate. How much you are getting? So I am getting 0.1125 meter. That means 112.5. Okay, so this much consolidation supplement will happen for this clay layer for an additional vertical stress increase of 160 kPa at the middle of the clay. Okay. So someone is having a doubt how this effective stress calculation is required for this course. Okay, so this is an example for that. Okay, so if you have no problem, then we can take our next problem. So next problem is taken from GATE 2023 examination, and it's about the shear strength of soil. So a consolidated drain triaxial test was carried out on a sand sample with the known effective shear strength parameters. C prime is 0 and phi prime value is 30 degrees. Now in the test, prior to failure, when the sample was undergoing axial compression under constant cell pressure, the drainage valve was accidentally closed. At failure, 360 kPa deviatoric stress was recorded along with 70 kPa pore water pressure. If the test is repeated without such error and no back pressure is applied in either of the tests, what is deviatoric stress in kPa in integer at failure? So please understand the problem statement very carefully, that we were trying to conduct a consolidated drain traction test. So as you know, there are three kinds of traction tests. What are those? What are the different kinds of traction tests? Consolidated drain, consolidated undrained, and unconsolidated undrained. So now for this problem, we were trying to conduct consolidated drain test. Now with the known effective shear strength parameters. So these are the drain shear strength values. 0, position is 0, and I prime is 30 degree. However, due to some problem, the drainage valve was accidentally closed. Because as you know that this consolidated drain, consolidated undrained, or unconsolidated undrained, the states, the classification of this test will depend on the drainage condition, whether the drainage condition is allowed or not. If the drainage condition is allowed, then the test will be drained in nature, otherwise it will be undrained. Now we were trying to perform drain test, however due to the accidental close of the drainage valve, this test now becomes an undrained test. So therefore, as a result, 360 kPa deviated stress was recorded along with 70 kPa pore water pressure. As you know that if the drainage valve was opened, then all the excess pore water pressure which was generated or which would be generated inside the sample would be dissipated due to the drainage condition. Now since the drainage valve was accidentally closed, so you will be getting excess pore water pressure, the generation of pore water pressure inside the soil sample, and it's 70 kPa. It's recorded along with the deviated stress at failure. Now, since our intention was not satisfied or fulfilled, so we are repeating the test again. And this time, we are ensuring that no such error should not happen. And we are not applying any back pressure. Okay. So in any of these tests. Now we have to report what would be the deviated stress at failure for this drain condition, consolidated drain condition. Do you get this problem? What is referring here? So two conditions are basically mentioned in this problem. The first one, undrained due to accidental closure of the valve, and then drain which was actually to be done or to be performed. Now for the undrained condition, what are the parameters recorded? The deviated stress sigma d, it's recorded as 360 kPa, and the pore water pressure U, that is 70 kPa. Now for the drain, what you need to calculate? You need to calculate where the drain shear strength parameters are known to you. The effective position is 0 and the effective angle of internal friction is 30 degrees, since this is a sand sample. Now how we can determine? So we can determine from this relationship that sigma 1 prime equals to sigma 3 prime tan square 45 degree plus 5 prime by 2 plus 2c prime tan 45 degree. And this relationship is basically derived on the basis of Moore-Coulomb failure criteria in the major principal stress plot. Okay, sorry, principal stress plot, sigma 1 versus sigma 3 prime, sigma 1 prime versus sigma 3 prime, and prime denotes the effective stress condition. Okay, so this is total minus pore water pressure. Now for the undrained condition. Okay, so first we'll be talking about undrained condition. Sigma 1 prime, it would be what? The effective major principal stress would be what? So it would be the total minus the pore water pressure. Yes or no? Effective
Yes,
stress.
sir. Yes.
So it would be total minus pore water pressure. Okay. Okay. So before going into that, one point I should mention here, that for this problem we can ignore the second part completely, since the effective cohesion is 0. Okay. So this part will vanish. So only we have to deal with this part. Okay. This part. Okay. Now coming to the sigma 1 prime, it's sigma 1 minus u, and you know what is the definition of the debitoric stress? What is the definition of debitoric stress? So the definition of debitoric stress is nothing but the difference between the major principal stress and the minor principal stress. Okay, you should know this concept. So when you will be performing the triaxial test, the first part, consolidation or unconsolidation, then the second phase is shearing. So during shearing, the confining pressure would be constant, and you will be applying the additional stress in the vertical direction or in the axial direction. So that will represent the major principal stress. So therefore, this sigma 1 minus sigma 3 will give you the debitoric stress. So that means sigma 1 would be sigma 3 plus sigma 3. Okay. So sigma 3 plus sigma 3 minus sigma 3. Now sigma D is recorded as 360 kPa minus U. U is also recorded as 70 kPa. So that means sigma 3 plus 290. And similarly, sigma 3 prime, we can calculate sigma 3 minus U. So the major effective minor principal stress would be nothing but total minor principal stress minus the pore water pressure. Sigma 3 we don't know, but the pore water pressure we know, sigma 3 minus 70. So therefore sigma 3 minus 70. Now we'll substitute these values of sigma 1 prime and sigma 3 prime in this expression. Okay, the relationship between sigma 1 prime and sigma 3 prime. Okay, so I don't have any space here. So here I am writing that sigma 1 prime, so it would be sigma 3 plus 290 equals to sigma 3 prime is nothing but sigma 3 minus 70 multiplied by tan square 45 degree plus 5 prime. What is the value of 5 prime? It's 30. So 30. And second part is already vanished due to the zero cohesion. So therefore, as you can see from this expression, the only unknown is, what is the only unknown? The confining pressure, the minor principal stress, sigma 3. So this is the only unknown in this equation. Now if you solve this equation, you can easily determine the sigma 3 value. So please solve and let me know. Please solve and let me know the value of sigma 3. How much you are getting? So tan square 45 plus 15, that means tan square 60. So it will be 3. This entire part will be 3. Okay. This part will be 3. So sigma 3 plus 290 equals to 3 sigma 3 minus 210. That means 3 sigma 3 minus sigma 3. 2 sigma 3 would be 290 plus 210. That means 500. That means sigma 3 equals to 250. Yes or no? Are you getting this value? 250 kPa for sigma 3.
Yes, sir, I'm getting.
Okay. So therefore, the confining pressure which was used to perform the fractional test was sigma 3 kPa. Okay, and it should be valid for both the scenarios, brain, whatever the scenario, unbrained or brain. So the problem was in the drainage valve. Okay, so for that drainage valve only, the initially planned brain test becomes unbrained. Okay, so sigma 3 value was 250 kPa. Sorry, so 250 kPa. Now we are repeating the test and we are ensuring that no such error will happen. Error in the sense the closure of the drainage valve, the accidental closure of the drainage valve. Therefore, if drainage valve is now opened and it's ensured to be open throughout the test, that means now it becomes drained in two sense. Okay. So again, we can use this relationship sigma 1 prime equals to sigma 3 prime transfer 45 degree plus 5 prime by 2 plus this part, and this part will not be valid for this problem because the prime is 0. But one important change or major change to this scenario would be there will be no U, no pore water pressure. That means sigma 1 prime would be sigma 1 and sigma 3 prime would be sigma 3. Whatever the total stress, that would be the effective stress for both the cases, major principal stress and the minor principal stress. Therefore, we know the minor principal stress, the total minor principal stress, 250. So we can easily determine the major principal stress for the drain condition. How? So sigma 1 prime would be 250 multiplied by tan square 45 degree plus 5 prime by 2, and this value is, the value of this part is 3. That means 750. So the major principal stress, effective major principal stress at failure for the drain condition is 750 kPa. Now what we have to report? We have to report the deviating stress. So the deviating stress, again, it is the difference between sigma 1 minus sigma 3, and that implies sigma 1 prime minus sigma 3 prime, because U, if you subtract U from both the components, so it will be automatically cancelled out. So that means 750 minus 350. Therefore, okay. So in this way, we can determine the deviating stress at failure regarding the drain condition or for the drain condition. And as I mentioned earlier, that this question is taken from GATE examination 2020. So now this is the last problem for this session, and it's a very straightforward problem, and it's related to the standard penetration test. So in a soil investigation work at a site, standard penetration test was conducted at every 1.5 meter interval up to the 30 meter depth. At 3 meter depth, the observed number of hammer blows for 3 successive 150 penetrations were 8, 6, 9 respectively. So what we have to report? The SPT n value at 3 meter depth. And again, this problem is taken from GATE examination 2020. Now what would be your answer to this problem? What is the definition of SPT n value? What is the definition of SPT n value? So it is the summation of blows, number of blows which required It is required for the last two successive penetrations. So if this is 150, this is 150, so this is first 150, second 150, third 150, then the number of blows required to penetrate last to 150 mm, that is total 300 mm, that will be the SPT n value. And why the first one, the number of blows required for 150 mm is discarded? So 3 penetrations are talked about in this problem, na?
The first one is seating.
Yeah.
Seating driver.
So since some setting error or this initial disturbance may occur at the field condition or in the field condition, so that's why the initial number of blows for a penetration of 150 mm is discarded. Okay, this is called something setting error. And the last two 150, total of 300 is added and recorded as the SPT n value, field SPT n value. So that means SPT n value for this problem would be 6 plus 9. Okay, is it okay?
Yes, sir, correct.
Okay. So now we'll end this session by taking one homework problem, and this homework problem is about a standard penetration test again, and it was carried out at a location by using a manually operated hammer dropping system with 50% efficiency. The recorded SPT value at a particular depth is 28. If an automatic hammer dropping system with 70% efficiency is used at the same location, what would be the recorded SPT value? And as you can see, this question was asked in GATE examination 2023. Now, two conditions are mentioned in this problem. So, the first scenario, manually operated hammer with dropping with efficiency 50% is used, and the recorded SPT value at a particular depth is recorded as 20. Now, in the second scenario, automated hammer dropping system with 70% efficiency is used. Now we have to report the recorded SPT value. What should be the recorded SPT? So any idea?
No idea, sir.
No idea. Okay. So for that you need to know that the field SPT n value is preferably expressed in terms of some efficiency. Okay, and efficiency in the sense, if you go through the lecture, so you will get the input energy, whatever is basically applied or imparted to the system, because how SPT test is performed, how it is performed. So some hammer is used basically, and with the help of some tripod stand, this hammer is basically dropped to penetrate the sampler and
Yes,
set the
sir.
at the required depth, and it will be having a free fall of something, I think 710 or something like that, no? 710 millimeter. Now,
Yes.
the input energy and the energy imparted to this system will be different. Okay, so that ratio will give you the efficiency. Now, you will come across that this SPT will be inversely proportional to the efficiency. Okay, this SPT n value, this will be inversely proportional to. Now, if we consider this situation 1 and this situation 2, and for the first one, it is eta 1 50%, and N1 this is 28, and for the second scenario it is 70%. Now what will be the N2? Then from this relationship it will be theta 1 N1 equals to. Now if we solve, you can easily determine.
Okay.
Theta represents the efficiency and N represents the SPT and N.
Right, sir. Thank you.
Okay, so with this we are at the end of this session. So just concluding this session. 1 minute please. Okay, so before concluding this session, so these are the list of reference materials and books which I think you have already gone through, because this slide is taken from the lecture materials. Okay, so these books you can refer for this course. And secondly, this is the information regarding next session. So we'll again meet on 6th August 2023 at 5 p.m. and I'll request you please go through the lecture contents which will be released for the next week or already released, I hope. So it will be easy for both of us to grasp the problems, okay, in a very efficient way. Okay, so thank you for attending this session and thanks a lot, and I will expect you to join.
Thanks a lot, sir. Thank you.
Thank you. Okay, then I am ending this session.